Okay, hello, welcome to stats video for chapter 9. In this video, we're going to go over examples that you should have already completed, 922 in the first part of 923. After that, we'll go through part B of 923, and then we'll skip down to the final section of the notes and do problem 932. For the new problems in the video, make sure you fill out your notes as you watch the video. Feel free to pause at any time. For the problems you should have already done, make sure you have done them before you look at the solutions. If you haven't done 922, for example, stop the video now, work it through on your own. We've got a quiz on Wednesday next week. The way to get prepared for the quiz is to practice these on your own, okay? But here are the solutions for 922. Make sure you check out all the steps. The biggest question I've had from students in the past here has to do with the hypotheses. Why is there a 1/12 for the null? Why greater than 1/12 for the alternate? Reading the prompt, we're assuming that each student who's watching these auditions has a randomized order. Okay, so there isn't any one spot in the ordering of the 12 videos that's going to be more or less likely to have the best acts, right? If there's no bias then, as far as the order that the tapes are watched, then we'd expect about 1/12 of students to like the first video, 1/12 will prefer the second, and the third all the way down to the 12th spot. So assuming no bias, the chance that people prefer the last video should be about 1/12. If there was a bias towards the most recently viewed video, then more than a 12th of viewers will tend to say, oh, I liked the last video, hence P greater than 1/12. Okay. Conditions, nothing really new or crazy happening here. Practice writing out the work. The formulas look a little bit complicated. It's totally fine to use fractional forms in the formula, keeping in mind that the calculator is going to do all the hard work for you anyway. Make sure you state an alpha. I don't think there was one given here, so state that first. Show full work for the p-value, even though the calculator is eventually giving you both the z and the p-value itself. As far as the symbol I'm using here in my inequality, you could use greater than or greater than or equal. Usually will line up similarly to the alternate. Just be careful. The alternate is never allowed to have a greater than or equal to sign. It has to be strictly greater. If you had an equal here, then if P is 1/12, technically both of the hypotheses are true, and that's kind of ridiculous. So watch out there. Make sure that you have failed to reject. Make sure that you have stated the null then in context. Okay, so that's example 922. 923, part A, this one you were working in groups at the end of class. It was two-sided. I think I gave the alternate in class. I think I pointed out showing the doubling to calculate your p-value. If you set your calculator correctly to do a two-sided test, you don't have to double the calculator answer. It has done it for you. So this 0.017 that the calculator should have given you, that's already been doubled. Our p-value is less than alpha. Therefore, we reject the null. Therefore, it makes sense to restate the alternate in words. But feel free to pause and check over the whole write-up. Part B. Well, it turns out there is a pretty strong connection between two-sided tests and the confidence intervals that we learned last chapter. Two-sided tests asked you to explore a certain distance from your p-hat in two directions. The p-hat is behaving like a point estimate. It already starts to feel similar to an interval. So there's an alternate strategy to conclude a two-sided test where you actually find a confidence interval instead of doing the traditional z statistic and p-value. So in part B, we're working through the same problem yet again, and we're going to get the same conclusion, slightly different technique. Here it says, construct a 95% interval. For these connections to work, connecting the interval to the test, there has to be a correspondence between the confidence level you pick and the alpha level you would have chosen in the significance test. Take a look at those numbers. I bet you can figure out what the connection is. Okay. Your confidence level plus your alpha adds up to 1. So in other words, a 95% interval goes with a 0.05 alpha. If we had used alpha of 0.1 for the significance test, we would need to use a 90% interval to get a corresponding result. If I used a 0.01 for alpha, we need a 99% interval. So make sure you have a correspondence there. But we used 0.05, so if we expect the same result using an interval, we want to go with 95%. The instructions say to check conditions. Obviously, I didn't write that all out. They're going to be the same as what we saw for the significance test. The only exception is, as you might recall, in an interval, we use p-hat in the normal check, which are slightly different values than the normal check that we saw in the significance test, but we still pass the check. So then comes the formula, confidence interval for a population proportion, plugging in info from the prompt. We're using p-hats through here. The z critical value 1.96 using inverse normal. And we end up with an interval. Now, how does that interval help us make a conclusion about our hypotheses from above? Well, it's quite simple. It's quite intuitive. There's a certain p suggested by the null hypothesis. Now we have an interval that's supposed to contain the real p. Does the p from the null land in the interval? Yes or no? Does 0.31 live in our interval? It does not. So we would reject the null. We are 95% confident the true proportion is between 0.32 and 0.47. Since 0.31 is not in there, we reject the null. And then you might actually finish with a conclusion similar to the significance test. So it's a cool little trick. If you have to do a two-sided procedure on a test, I would stick with the conventional significance test unless directed otherwise, but you may very well see questions on the test that ask you about how would you use a confidence interval? What would be the formula? There might be a multiple choice question themed around it or something like that. All right. Yeah, so we're gonna now skip into 9.3. That's the end of 9.2. And we'll save some of these examples for class on Monday, maybe even Tuesday. Unsurprisingly, 9.3 has us now looking at significance tests for claims about means. We'll see certain ideas carry over. We'll see certain details being a little bit different. The big thing to remember, similar to last chapter, if we're going to deal with means, we end up using a modified standard deviation involving SX instead of a population deviation. And for that reason, we use the t-distribution once again. So we do not have a z-test statistic, z-score, we have this t-score, okay? But the template is still similar to previous things we've done. We take our x-bar from a sample, find the difference with the hypothesized mean. How far is our x-bar from what we think it should have been? Divide by a sample standard deviation, s over root n. And then we use TCDF to figure out what's the likelihood that a t-statistic could be as far as ours from where it was expected to be. Calculator's going to do a lot of that for you, okay? We're going to skip 9.3.1, save it for class. We're going to look at a single write-up in this video, and then there's a follow-up question. So 9.3.2, sensory deprivation tanks. Haven't really tried one myself, but I'm curious. We've got Tanquility, a local studio offering experiences that's supposedly a 50-minute session. The implication being that 50 minutes is kind of the amount of time necessary to achieve tranquility. Okay. But a local critic feels the sessions are shorter than advertised. That's a clue about hypotheses right there. Helpers purchase sessions randomly. What do we got? We got some raw data here. Okay. Is there evidence to warrant a suspicion? We've also got some graphs for that data. It's a little hint as to where we're headed. First step for mean problems, we're going to see hypotheses. We also have to define a couple things. Again, I think if done properly, you can embed your population of interest into your definition of your random variable X. Okay, so it's a population of sensory deprivation tank sessions. We're measuring the length of those sessions. So it's somewhat implied in here that sessions are the population. We're interested in mu, the mean session length. And the natural null hypothesis would be, let's assume that on average, the lengths are the 50 minutes. Alternate, maybe we actually suspect mu is less than 50. All right, so that's your first step. Writing all that down. Step 2, testing a claim about a population mean, and same as last chapter, standard deviation, not known. That's why we use what's called a t-test. I call it a one sample t-test for means. That's what we would write for part 2. Conditions, random condition. We do have the word random in the prompt, so we're good to go there. Excuse me. Independent condition, 10n check. Do we think there's more than 120 sessions in all? I think that's easy to assume. Normal condition. As you recall from chapter 8, there's a few different ways this can play out for confidence intervals. So it's the same for significance tests. And unfortunately, we have the worst case scenario here. There's no indication in the prompt about distribution of session lengths being normal. Okay. We also don't have a sample size bigger than 30. So we have to consult some graphs. Luckily, for this problem, the graphs are provided, so don't worry about playing around on your calculator. There's a few things to look at here. Got a dot plot, box plot, normal probability plot as well. All we need to do is describe the plots. You might as well describe all the plots that are given. They all contribute to our conclusion here. Normal probability plot, it's been a while since we did these. All you care about is whether or not the pattern looks approximately linear. So that's what I'm going to say. Normal probability plot is fairly linear. Dot and box plots don't show us extreme skew or outliers. Therefore, there's no evidence of non-normality and it's safe to proceed. I'm not going far enough to claim that I have achieved normality of anything. I don't need to go that far. I shouldn't go that far. Just say that it's safe to proceed. Okay. Yeah. Calculations. I actually am noticing here I've got a small error. I should have stated an alpha. I don't believe there was one in the prompt. But regardless, you should state alpha over here before you get into your actual calculations. I clearly ended up using 0.05. All right. You'll also notice I've got some extra sample statistics. I got these from a calculator. I don't have a calculator hooked up to the Zoom here for the video to show calculator stuff, so I think you can probably figure out some things on your own. And if it's not as intuitive as I'm suggesting, then I can show it in class real quick on Monday. But what's happening, you're you're putting your raw data into list 1 in your calculator. And then once you've got it, you could use one variable stats on list 1 to figure out an X bar and an SX. Okay. Remember, we want to write down degrees of freedom as well. When we're using t-tests, 1 less than sample size, make sure to write that down. Okay. Work, actual calculations, T formula, and then your p-value. I'm still writing out the general formula. I should zoom in a little bit here. And then I start plugging numbers in. I'm plugging in the X bar from my calculator, 50 from the null, standard deviation from the calculator. Make sure you use the SX divided by root sample size to get a T. At that point, you're going to go to the actual stats app. Again, I don't have it hooked up, but if you're working off an 89, you would go to F6, which is our test menu, and it's going to be the second choice in there. It's called t-test. When you open that up, you'll see the calculator wants to know data or stats. This time we're using raw data, so you would choose so. Once you get into the t-test inputs, it wants to know your null hypothesis. So the first input for this problem is a 50. The next input beyond that, it wants to know what list you're dealing with. So tell it list 1. Below that, there's a frequency cell, just ignore it. Below that, you do have to pick the proper alternate hypothesis. Remember, we want a less than hypothesis. Make sure that that's chosen. And when you press enter, eventually, actually, turns out we didn't have to do one variable stats to write some of these values down. It does give you all of that in the t-test. It gives you your t statistic in there. It gives you your p-value. It reminds you about degrees of freedom. It does give you an X bar and an SX. Okay, so you can actually run the test in your calculator before you write down any of the work, and then just use the calculator results to guide everything that's on the page here. Okay. Make sure you have a less than symbol in the work for your p-value matching up with our alternate hypothesis. Conclusion, since the p-value, restate it, is less than the alpha of 0.05, therefore we reject the null in favor of the alternate. The mean tank session is actually less than 50 minutes. Okay. Follow-up question part B. I referenced this the other day in class, questions about error or common follow-ups. Given our conclusion, given that we rejected the null, what type of mistake might we have made? Well, there's only one type of error that comes from rejecting a null, and that would be type 1. We reject the null when actually it was true. Explain what that means in context. So that's what I'm writing out here. We concluded the mean session is less than 50. If the mean is actually 50 minutes, we made a type 1 error. Consequences of that, we may report our findings, could lead to a reduction in business for this company, which could hurt their business, lose money, go out of business, something like that. Make sure you give us somewhat specific real world consequence. Okay. I think that's enough for the video to get us a little bit caught up. We'll save some stuff for Monday, maybe even save an example for Tuesday. Thanks for watching. Feel free to email if you have any questions.